I will manage, sir.
Yeah, recording has already started, Bharat. So you can start from this point. So in
Okay,
this
sir.
in class, I completed still procedure. So they have basic idea about RISC-V. So you can
Okay.
explain how they can start programming in RISC-V simulator.
Yes.
Okay. And
Okay.
if there are a lot of queries, then maybe you can note all these queries and maybe you can reply later because I think you have to finish it by at least now it is 6, so at max 7:30, not more than that. You have to finish it and try to answer their queries. But if the queries are more, then maybe you can record those queries and maybe we can reply them later also.
Okay. Okay. Okay.
Okay. Okay, and the advantage is here the video is we are recording the lecture. So after if there is any doubt or anything, then maybe they can watch this video again.
Yes.
Okay, so over to you. And now I'll not say anything, and maybe I'll not listen also. In case of any emergency, please call me.
Okay. Okay. Okay, sir.
Okay.
Thank you, sir.
Okay.
Yeah. So, hello, class. I am Bharat Bisht, MTech final year student of Computer Science and Engineering. So, I will take this RISC-V tutorial session. So, our basic aim of this tutorial is to make you familiar with the with this RISC-V simulator we will use. And so, first I will start with the basic of this online RISC-V simulator. So, we'll use an online tool for that, and then we'll discuss with some problem examples, like some problem codes, like if else statement, and some loop and procedure calls, etc. And so yeah, we'll start in this way. And if you have any queries in between, you can raise your hand. So yeah, so uh, let me share my screen. Is it visible to you?
Yes, sir.
Okay.
Yes, sir.
Okay. So, as I already said, this is an online simulator tool, so we can use this simulator from any browser. I am using this Google Chrome. So first we have to search here for uh, the Venus web terminal. You can search this web terminal. So here you can see that the very first link is venus.cs61c.org. So we'll use this simulator, or yeah, you can use this link. So this is our online simulator tool for RISC-V. We will use here these two windows only, editor panel and this simulator. So in editor panel, this RISC-V simulator has two panel, editor and this simulator. So in editor, we'll use to write our code, and in simulator part, we'll see all these things, all these how the values are stored in the register and memory and all these things. So we'll discuss with some examples. So yeah, so here I have already written some program for you. Let's say the first one is if then else. Yeah, so it is an if else program, simple if else program. So I'm using this editor, and I am writing here this program. So this is if I write this program in C for you. So this is simple if, and there is a number uh, x, let's say it is x, and if this x is less than 0, and then we can say return or display, we can say anything, return -1 because it is a negative number, and else for non-negative number we will return 1. So this is the simple if else program. So how when we'll compile this program into this C program, then it will look like this. In the assembly code, we'll write this code for this program. So we'll see line by line. The first one is we are using a temporary register x5. So I am here using 0. You can use anything. This is a basically a number we are going to use. Let's say number is equal to 23. So and I am storing this number into x5 register. Then in the next instruction, what we are using is branch less than. If x5 is less than x0. So x0 is a register. We will discuss it later. X0 is a register which stores always 0 value. So we will compare this x0 with our value number x5. So if x5 is less than x0, then we will jump to the target location. So target location is here is a label. So we will jump to there. So if this x5 is less than 0, means it is a negative number, then we will jump here, and I am adding I am using this add immediate instruction. I am adding x10 to this 0 register, and I am adding -1 to it. -1 means, so the value of x10 now will be -1. And if the number is positive, then this branch instruction will just follow the next instruction. So then I am using 1 here. I am assigning 1 to the x10 register, and then we exiting, so that we will not jump to here also. So then I am using exit here. So I am running this program. So we'll go to the simulator part, and first we'll click here assemble and simulate from editor. So I am clicking in it, and we'll just run this program, and you can see that here is an exit code 1. So I will tell you all this meaning of all this. So when I am, yeah, I will come to that. Yeah, in this hashtag is used for commenting these, for comments we'll use has. Then yeah, when I am clicking to this, so it means that our program, our RISC-V program is mapping to the memory, main memory. So when first when see this at this point, I have not clicked here. So you can see that all these registers are by are in its default values. These are the registers. So let first discuss all these register and memory section. Okay. So there are 32 registers in RISC-V, 32 integer registers and 32 floating point registers. So these integer registers are 0 register, which is starting from x0, x1, x2, and till x31. So there are total 32 registers. So these all these registers have their different meanings. Let's say this is a fixed register. We cannot change the value of this register. So let me try to change this the value of this register. Add I x0 x0. Why is x2 only filled? Yeah. Okay. So x2 is a here. S2 you can see it is a stack pointer. So it is pointing to the address of the stack pointer. So the base by default address of the stack pointer is a this one. So and that's why it is pointing to this location, and the global pointer is pointing to this location. You can say you can see that here is one starting from 1000, and these are all the default values of these registers. So if I am trying to add something in x0 register, x00, let's say 5. So I am trying to add 5 in this x0 register. Now I am compiling it and run it. So you can see here there is no change in 0 register. And if I use some another register like x1, then the change is reflected to that register. You can say x1 register is also 000. Now I am changing the I am running this, and it is now changed to 5. So now you can understand that we cannot change the value of this register x0. Another register is RA, return address. So basically RA, SP, these are their standard names. The register are x0, x1, x2, these, and these are just their names, RA. So you can use either one, RA or x1. In both case it is fine. So the RA is means the return address. When we are returning from some procedure, some function, then we'll use this register. I will come back to this again when we use some program of procedure calls. Then this is stack pointer. So stack pointer points to the first level, very first memory location of the stack. So for this stack pointer and what is stack pointer, you should know this diagram. Let me show this. So are you familiar with this diagram? Memory allocation. You can type in chat box. Okay, no. So okay. I am telling you. Yeah. So when we compile a program, let's say our basic C program, then when we execute this program, means run this program, then it maps firstly is it come map from secondary memory to the main memory. So this is how it mapped to the main memory. This is our main memory. You can see here. The first part is reserve part. Reserve part means at the bottom you can see that the reserve part means it is reserved for some OS functionalities. We cannot do something here. Okay. Then there are 4 more parts: text, static data, dynamic data, and stack. The text, all our program, all our instructions are stored in the text section, text part. And all static data means all our let's say global variables, and what is global variable and static variable in C. So all our global variable and what we can see static variable are stored in this data section part. And this dynamic data part we also call it heap memory. You have heard about it, I think. So in heap, when we allocate some dynamic data allocation, when we use dynamic data allocation, then these variables are stored here in dynamic, and stack is used for like function calling. So this is the default address for stack. So that's why in this stack pointer, the value is this one. So these are 4 sections: text, static data, dynamic data, and stack. These stack and dynamic data has no fixed division here. We can grow from bottom to up in dynamic data and top to down in stack. It is reverse kind of thing. And in all other static data, text and other thing, we'll use from bottom to upward. We'll use in this way. So we'll see all these in our simulator here. So in memory section, this is our main memory. We'll see all this. So here you can see, I need to zoom it. Yeah. So you can, are you able to see? So there are 4 sections: text, data, heap, and stack. Heap is our dynamic data part. So let's say I'm writing this program again, and when I click to this, what I said is all our instruction and static data or global data are coming to this memory. So it maps to the memory. So here this is the text part. If I jump to the text part, So this is default one. So we can see this is the machine code for these instructions. These are the instruction add I, BLT, add I, BQ, and these are their corresponding machine codes. And this is the program counter values. So in program counter value is this one, the address. Program counter means the address of that instruction. So in this 00 address here, the first one, then because it is of 32 bits, we are dividing it into 4 bytes, 1 2 3 4, and we are assuming that the that this memory is byte addressable, like it is the first address, then this is second, third, and fourth. So that yeah, and the 4 bytes makes a word. So a 32-bit word. So here we can see that this is the machine code, and the code you can see here 93, and yeah, it is in hexa. So 5D02. Okay, so in 93 here, it is corresponding to this 5D. If I convert this 5D, so it will be this 93, then 02, this 02, and 0000. Yeah, this 00. Then you can see this 63 here. It is 63 is here. Then C6 is here. Then 02 and 00, 02 and 00. So all these machine code, what I mean it, all these machine code means our program. This is our actual program, and it maps to the text part of the memory here. This is the text section, and the data. I am using okay. I have not used any data section here, so I will later use this data part. So all the I have to jump to the data section. So all this data part, like if we initialize any static data or the global memory, so it will map to this location from 0x10000. It is also the global pointer, we can say, the value of global pointer, because I said that all the global memory or these global variable and static data are mapped here from this toward to upwards. First is here, then here, then here, then here. Okay. Then you can see the third is heap part. You can jump to here, heap and the stack. Stack is from top to bottom. Yeah, I have jumped to stack. So this is the default value of the stack, and we'll use stack from up to down manner, as you can see here. So these are the 4 memory parts. Then if you want to jump to any address, you can type it here, and then you can jump to that memory location. And if you go from step by step upward direction and downward direction, then you can use these two buttons. Okay. So this is all about our memory, main memory. Then OXC. So 0x means this is a for every hexadecimal number we'll use 0x. 0x represent it is a hexadecimal number. Okay, it is 0x0 means it is hexadecimal number 0. It is hexadecimal number 4. It is we are incrementing by 4 because you can see here in memory section each word is of 4 bytes. So if we go from here to here, we have to increment by 4. So we are incrementing by 4 for all PC instructions. It is 0, then 4, then 8, then 12, and 12 is the hexadecimal value of C. Then 12, after 12 it is 16, and 16 the hexadecimal value of 16 is 10. So all you can see here 0x 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 means it is a hexadecimal value. Okay. Yeah, here also whenever you see okay. What are plus 0 plus okay, these 0 plus 0 plus okay. So let's say this is an address 7FFF 7FFFC. So we will add plus 0 in it, and this is the address of this byte. So these are for the address of each byte. It is the address of the first one, the basic one, and we will add 0 in it. So it represents this one. When we will add +1, then it will represent the second byte. When we will add +2, then it is the third byte and fourth byte. So yeah, you understand? Okay. So we have understand this, and uh, after this, uh, we have some kind. We have assembler directive in this RISC-V, and there are many assembler directive. So we'll use dot data. I'm writing here all the assembler directive dot text, uh, dot word, and sorry, dot word. Okay, sorry. All assembler directive are dot data, dot text, dot word, dot we can say byte. There are many one. Dot byte, dot skiz, and so yeah, there are many one. So these are the main SKZ. Okay. So the data, it represent that assembler directive is something which direct to the assembler that this is a data section part. So we'll declare all our global variable into this part, dot data part, all the global variable and static variable, and we'll write our code into this dot text part. In the first program you have seen that I didn't use any of these. So by default this is the dot text section. If I do not use any of these, so this is the dot text part. Then if I use these one, then for dot data it is used for declaring the variables, and for dot text it is used to write our code. And dot word, it direct to the assembler that it is a word means it is an integer of 32 bit. A byte is represent that it is an integer of 8 bits. 8 bit is 1 byte. So yeah, and we can use dot sort also. Sort means it is of mm, dot word dot sort is of I think half. We can use half here. Yeah, half is of word is of 32 bytes bits, and so half is of 16 bits. And we can also use double word, dot d word. So dot d word is for this. If we use 64 bits, so it represents a 64 bit integer. And skiz is represent the sky value of something. Like when we use string, then we will use this assembler directive for string values. So let's say in our data section I am using a string of str, and this is the way to declare variables str, and we are using dot skiz, and the value is let's say my name Bharat. So when we simulate this, so in the memory section you can say in the data part, the data section part, uh, in this address this is the sky values. 62 is the sky value of b, 68 is the sky value of h, then 61 is the sky value of a. B, h, a, r, a, t is simple. So we can change this value. It is by default in hex. We can change it to decimal, unsigned, and sky also. So if I change it to sky, you can see here. Okay, why it is. Yeah, so now you can see here Bharat. So the this this str string is mapped to our memory in the data part, in this data part. So this is how we can declare any string. And if we use here dot word, and let's say it is an str is an array of integers, 30, 23, any number. So when I use this, so you can see here, I have to convert into not ASCII in decimal values. So you can see there this 30, then 23, 53, 63, and this, yeah. So, and here you can see it is consuming the whole word. Word means these 32 bits. It is consuming 32 bits. That's why all other are zeros. And this is consuming the whole 32 bit, 23, 53. If I use here uh, instead of word, if I use byte, then it will assign these values byte by byte. Only one byte it will consume. So here you can see, yeah, now it is consuming only one byte, 30, 23, 30, 23, 53, 63, and so on. If I use here half, then it will consume 2 bytes for that. So, and so on. Yeah. So we have discussed this also. So we have already discussed this if else. Now let's say we'll discuss this loop realization problem. It is we are just realizing a loop, for loop, for sum of element of an array. So I'm copying it in editor part. And one more thing, if you want to save this program, so I have written this program, and if I want to save, we'll just press Ctrl S and the name of this file, like file1, and save. Then it is stored, and it is stored in the extension you can see here is .s. The file is of .s extension. .s means it is a this assembly language code. So when we compile a C program into so finally it is converted into a executable code .exe. There are various phases in between. First, the compiler, what compiler do is compiler convert this cpp or .c file into pre-processed file. It means it pre-processed the header file, and all it removes all the white spaces in between, and these things it do on these head all it uses all macros. So it is pre-processed. The extension of pre-processed file is .i. Then this pre-processed file is converted into assembly language code, this code, and the extension for this file is .s. So I am suggesting you, if you write any code and you have to submit it to as an assignment, so you submit it in .s file, so that it is easy for us to have evaluate. Yeah, you can use .txt also, but it is good if you use .s file. Then after this, so let me clear this. Then another program is this one. Okay, so I already pasted in this editor section. So here you can see I have used .data and .txt. In .data, I have initialized these variables. Array is a array of these. These are the elements of the array, and n is the length of this array. So why I am using the length of the array? Because we don't know where to stop. Here, if we parse this array, so we have to know that where to stop. So that's why I am using this. So let's say I convert this into C first, then you will understand better. It is for int I is equal to 0, is less than 10, or we can say array size and I plus plus, and we are summing it like sum plus is equal to this array of I, and this is our array, int array is equal to, these are the values 3 4 etc. This is the value of our array. So when we convert, and this is our typical C program, and when compiler converts it into assembly code, so what it does, it also store the number of elements in this array. So that's why I am using here n also. So it is not like it check it into runtime. So it store the size of array also. So here to check that these many elements are into this array. So these are two things. Then in dot text part, we can see that this is our actual instructions, actual code. So in this, I am using load address. So uh, I am loading the address of the base address of the array ARR into X5. X5 is a register. So yeah, first tell me about these registers. I have not tell you. Okay. So and this is stack pointer. This is global pointer. Global pointer points to uh, the first address of the this data section, and there is a thread pointer. These are the register, temporary register T0, T1, T2. These three are the temporary register. There are different use of different register, but we can use any one. But it is suggested that for temporary to store the temporary values, we'll use these temporary register. To store the saved values, we'll use saved register. This S0, S1, these are the saved register, S0, S1, and A0, A1, A2, A3. These are the arguments to save the arguments of any. When we call the function call, then we'll store the arguments in these registers. And A0, A1 are also, we can say that there are whole list of these functions. So I will share this file to you. uh, Here you can see any all these things. So this is the X0 register. It always, it is the store the constant value 0, then return address, stack pointer, global pointer, thread pointer. Then from T0 to T2, these are temporary register. S0, S1, these are saved register, and this is X8 is also a frame pointer. We can use it as a frame pointer. Then from A0, A1, and A2, A7, these are function arguments, and A0, A1 are also used as return values. When we return from a function, then this return value, what we will return, is stored in this A0 or either in A1. So these are the all different registers. S2 to S11 to FT11. So these are all the registers. So we can use any register, but it is suggested that for temporary register we'll use this temporary, because if I use stack pointer for some calculation, then what will happen is we can our stack pointer, the value of these hold by the stack pointer. So we'll lost that stack pointer. So that's why it is suggested to not use these register, and unless and until Hello. Yep. Please wait. I think there is some network issue from my side. Give me 2 minutes so that I can fix it. Hello. Am I audible now?
Yes, sir.
So sorry for the disruption. Actually, my Wi-Fi is down today, so I have to use mobile network. Okay. So let me share my screen once again. Yeah. So we are here. Yeah. So I am here. This. So here we can see that I am loading this base address of the array into x5. Then I am loading the value n value. This is the size of the array into x6. These are temporary register x5, x6. Then I am initializing. So here you can see I am in for loop. What we do? We initialize I to 0. So I am initializing x7 to 0. Then I am beginning begin. This is a label. So the label we will use as this way: begin, then colon. So begin means the loop is started from here. So first it will check for the condition. If branch greater than, I am using branch greater than. If x7 register is greater than x6, then we jump exit. Means if I is greater than x, this 10, value 10, and the value x6, x6 is the array. So if it's greater than or equal to, if it is the I become 10 or greater than 10, then we'll exit the program. We'll go to exit. Exit is the last level here, you can see. So yeah, and then um, in this loop what I am doing, so I am loading the value from in this array. So x5 is the address, you can see here. So I am using 0 for offset. So it will load the first value from the array and store it into x8. It is another temporary list. Then x8, I will add x8 into x10 and it store it into x10. So I am using this for the sum, to store the sum in the x10 register. Then I am incrementing the array pointer x5. Then I am incrementing the I x7. So and then again beq x0 x0 means it is always x0 is always equal to x0. Then it is a uh, it is a conditional jump, but it is always true. So it is always go to the beginning of the loop. Then it will happen again and again. Then finally when we parse all these elements, then we'll go to the exit part. So this is the program. Now we'll run this program. Then if we want to run this program step by step, like instruction by instruction, then we'll use this step here. You can see the step button. So we'll use step. So you can see the program is executed step by step. Here you can see this green line. And if we want to go to the previous instruction, then we'll use previous. And if we want to reset that program from the initial to the initial position, then we'll use reset. And if we want to run the whole program into one go, then we'll use run. So and in this way we can run. So I am running this program, and here you can see the exit code error exited with error code this one like 24. So this is not any error. So it represents the value of x10 register. Whatever the value of x10 register, it will show here. So I am running it again. So the final value of x10 register is 24. This is the sum of the array. You can see here the sum of the array is 24. You can sum it up, and then this we are storing this into x10 register. You can see here what is AUIPC. Okay, this AUIPC. Okay, I will come to this. So this is 24 is storing here in register x10, and when we run this, we'll see the value of x10 here. If the value of x10 is 0, then we'll see here exited with 0. Then you are asking for AUIPC. So it is an instruction. So what is LA, load address? Load address is not a basic instruction. Basic means like it is a pseudo instruction. Pseudo instruction means it is composing of 2 or more instructions. So you can see here, this is the original code and this is the basic code. So original code is LA, what I am using here, LAX5ARR. So it is LAX5ARR, and the basic code for this these two are the same instruction, but it composes of 2 basic instructions, AUIPC and AI. So the LA instruction, load address, is these 2 instructions. So AUIPC means add upper immediate into PC. So it add so let me so AUIPC. So AUIPC, what it does, let's say our PC value is 0x00000004. Let's say this is our PC value, and I am using AUIPC into some register x10, let's say, and I am using let's say some value 0x4. It is a hexadecimal value, so I am using hexadecimal because the calculation will be easy. So I am adding this into AUI into this x10 register. So what AUIPC does, you can okay, it this is the our PC value. So it add this value into the PC, but not here, not in the basic. upper immediate means we will separate these three portion. It is the upper value of the register, and this is the lower value of the register. These 3 bytes and these 5 bytes are the upper value. So we'll add this address, this offset into here 0x 0x000004. We'll add it here. Then the final answer will it will be 0x 0x000004. Yeah, it will become this. So this is the AUIPC. How it is determined which register value will be exit code. Yeah, exit code. It is all. I am what I said is it is always the value of X10 register. Yeah, here X10 is for the return value. So it is showing the return value of the function only. So we have run this program also. The result of this is 24. So let me show you the AUPIC. Add x0. I am using a just an instruction. It does nothing. Add x0 x0 x0. It is just an instruction. And now I am using AUIPC. And I am using in X10. I am adding 0x4 for this example. I am using AUIPC in X10 and I am adding 0x4 into it. So now this is the from in this instruction, what will the value of PC? It is 0. So that's why I am using this. In this instruction, when this instruction will execute the second one, then the PC value will become 04. What I am using here, the PC value is 04. So and I am using 04 into it. So the answer, we can run it, and the answer of X10, let me convert it into hexadecimal, is 0000404, which I have, yeah, 0000404. So this is the AUIPC instruction. You can see all instructions are here also. This is a instruction sheet, RISC-V instruction sheet. What does upper immediate means? I can't understand. Upper immediate means I am adding this value to the PC. I am adding this offset, but I am not adding it into the lower value of the PC. I am adding it into the upper immediate part. Upper immediate means this, in this portion. We will divide it into 2 parts. These are 3 bytes. Not 3 bytes. This is 4 bit, 4 bit, 4 bit. 12 bit are here, and another remaining 20 bits are this one. So we'll add our offset into this 20 bit in the upper immediate part. Upper immediate part means the upper values of the register, not in this location, not in this part. So yeah. So if we use load upper immediate, so it is the same, but here we are not using the PC value. Load upper immediate is the, we are using let's say in X10 we are using we are adding 0x4, this value. So it will add 0x4 into the upper part of the register after the 3 bytes. Let me run this program in X10. Now you can see that here the 3 not bytes, these 344 bits means these 12 bits are 0, and the remaining bits I am adding 4 to here. So this is the load upper immediate. We are adding 4 into the upper part of this location. Okay, so these are LUI and AUPIC. Then I want to show you some more. Okay. Let's say we'll use this program now. Sorry. This is a program for procedure calls. So in procedure calls, what I am doing here is simply adding I am adding two values with the help of function call. Let me go down. Okay, this is our function int add, and I am adding x and y and returning the sum of these two values. So how will we write the program? First we will call main, then let's okay. This is function definition, we can see, and we'll call main here. Our main function is here, and I am let's say int a and b. These are two integers, and I am assigning a to 23 and b to a to 23 and b is equal to 11. Okay, now I am calling this function add, and int c is equal to add a comma b. I am using this one. Okay, so this is our C code for what I am using in here. So we will realize it into this assembly code. First, I am declaring two variables a and b, and I am using 23 and 11. Yeah, these values a is equal to 23 and b is equal to 11. Now, this is add. I labeled here add. So what we are doing? This add function, it is a you can say it is a procedure call. So this is a function to add two numbers. Then first in the data section we see here I have defined two a and b as 23 and 11. In the text part, first I am calling main function. So when we execute a program, first what happen is it execute the main program from the main program. So our main program is here, let's say here, this main label, from this main label. So I have used this bq x0 x0 so that we'll jump to that main this main function, and will not execute this right now. So we jump to here in main function. Then I am loading in x5, I am loading the variable a, and x6 I am loading the variable b. I am using here temporary variables. You can see, yeah, I am using temporary variable for a and b. Then what I am doing, I am so what I am doing, I am putting these values. So because these are the arguments a and b, we are passing argument to this function. So that's why I am using x12 and x13 here. What x12 and x13 means, you can say here, you can see here in this x12 and x13 are the a2 a3, and a2 a3 means these are the argument registers. This is used for when we call an function. I am using a function, we can use another also, but this is the suggested way to use these registers. So I am using this these two are argument registers. I am using this and assigning value of x5 into x12 and assigning value of x6 into x13. You can see it. Then I am calling the function jl with the help of jl. Jl is the jump instruction. So I am jumping here, jump and link instruction. So what it does, it jump to this location. Add is a function here. You can see I've created in this above. So I am calling this function, and I am the x1 here. It assign the next address, the address of the next instruction here into this x1, so that we can uh, come back from this function in the later. Yeah, when I am calling this function, we'll jump to here. Then after executing this function, we have to come back here. After this, yeah, you can see in here, I am calling this function add. So I am jumping here. Now after executing these lines, I have to jump back there in this after this instruction, after this statement. So that's why I am JL instruction store the very next instruction here, the value of very next instruction, and it stores this value into x1. Why in x1? Because x1 is the register. You can say here x1, it is used for return address RA. So you can use another register also, but it is a suggested way to use these registers. Like when we use x1, when we use x2, when we use x3. So I am using these return address. So here you can see in x1 the very next address of this instruction after this instruction is stored in x1. Then we jump to here in add, uh, in add part, in add procedure, what we can say. And let's say ignore these two values, these two lines which I have commented. Ignore for that now. Now I am adding x12 and x13, which are our argument variables. So we have passed these through these x12 and x13. Now I am adding these x12 and x13, and I am storing the result back into x10. So x10 is used for to return the value, for return value. So that's why I am using x10 here. And after that, after adding these values, I am returning back to that location from where I have called this function. So it is used for JALR is used for jump and link register. Jump and link register means here you can see JL. What is the difference between JL and JLR? These are the similar one, but in JL we'll use the this label. We'll use label here, and in JLR we will not use any label, but instead of that we'll use the register value. So I am using x1. X1 is the this register, the very next instruction address of this. So here you can see x10 is storing the value of next instruction. Now x1 has the value of next instruction. Then I am calling the next this return address from here. I am adding 0 to it, and I am calling this. And this for the next instruction of this one, I am using x0 here. X0 so that we don't need the return address of this function. Return address means that very next instruction of this address, because it is of no use. So that's why I am using x0 here. Now you can see that after executing this instruction, we'll jump here in the exit level actually. Now and the program executed. So we'll compile, we'll run it step by step. Here first I am from this instruction, I just jumped here in this location where I am loading a value a. It is just a main function. So I am jumped to the main function, and I am loading the value of a into x5. Then I am loading the value of b into x6. So you can see here also I am loading the value of x5 and x6 here, a and b. So these are the hexadecimal values. when I convert it into decimal, x 5 and x 6, 23 and okay, let me this 23 and 11. You can say these values are loaded into the register. Now, after that, I am using x12 and x13, these argument variable. I am putting these 23 and 11 in those argument registers. 12 and 13. Yeah. So in x12 and x13, there are also 23 and 11 here. After this, I am jumping to add these two arguments, a and b. So I am adding these two. So we'll jump here from here to the add one. Let's say next step. So here, this is the add one. So now we are using x12 and x13. We will add these two because these are the arguments, our arguments, and result will be stored here in x10. So here is the x10. So step. Now the sum is stored here, 34. You can see. After that, we'll call JLR, and we'll come back from we call that this function. Next step, then this is executed, and the return value is 34. The sum of these two values. We can sum these values in just 2 lines also, but I want to explain you how the program works when you call these procedure calls. So that's why I use this example. Now, what is these two things which I have commented? So let me uncomment these two. So when I call this add function, the x1 hold the return address of that caller function, which called this function. Okay, so this is the return address. Actually, if the add program, if this function is let's say too big, or it is calling some another function also, from here we are jumping to another function, then we have to use this x1 for another function. You understand? So we are using x1 here again. So it's not like we'll get the same value from x1 when we'll call this JLR. We can change the value of x1 in between. So that's why we will use stack here to store the value of x1, and I am storing the value of x1 into stack. So here x2 means the stack pointer. So in the stack pointer, I am storing the value of x1 so that I can use later, and I can change the value of x1 in this program, in these instructions. So I am storing the value of whenever we call a function, I am calling add. So we'll store the value of this x1 into the into stack, our stack. When we call a function, then a stack frame is allocated to that function, and in this stack frame, let me show you this. This is the stack frame. So all arguments are here, all saved register, all local variables you can see in this stack frame. When we call a function, then this will assign to that function. So we'll store in this, and here is our stack pointer. We'll store, we can store the return address here also. So when I am storing the return address here in our stack, then I am performing some action, and last before calling this JLR, what I am doing, I am loading that value from the stack, and I am loading it into the x1. Then I call this JLR function. So it will use in when you will use some recursion kind of thing. Then you have to call one function from another, this kind of thing. So this is what I mean. So you can see it here in simulation part. I am step. So after calling this function add, here. First, you can see in memory where is the stack pointer is here. So actually stack pointer point to here, this location. So this 48 is the address of x1. Step back. Wait a minute. So it is firstly it is 0. There is nothing here. When we call this function add, yeah. So I am storing the value of x1 into the stack pointer. After executing this instruction, you can see here 48. 48 is the return address of the caller function. So I am storing it into stack. Now I can change the value of x1 because I have stored it into the stack. Now I can change the value of x1, and when I return back to that to the caller function, then I will load this value from the memory, stack memory. So yeah, here I load this x1. I am loading this x1 again. Then I am using all this, and the program is same. I am just wanted to show you how you can call, how you can use this stack pointer and all these things. Now let's say and what remain here. Okay, and one more thing. If you code in this assembly language, so here is also a kind of you can use debugging. Debugging how you can use breakpoint here. After assemble, you can use breakpoints so that when we use when I will use run, the program will stuck here at this point. It will stop here, run, and it is stopped here. You can see, and I can use many breakpoints at a time. So this is just for the debugging. If you want to debug your code, you want to check at this particular point what is the status of your memory and what is the status of your registers, then you can use this debugging kind of thing. Okay, so this is debugging, and what else is remaining? I have some more program also. Okay, this is one program to check whether the number is even or odd. So how will we use this? Invariance. Okay, so there is a number n here. So we have to check that this number is even or odd. So how we'll check this number? So basically, let's say make it simple, not 31, make it 5. Okay. What better I will explain now. So the value of 5 is 0000101. Let's say there are many zeros. It is a 32 bit. Assume it is 32 bit. So how? So first, what I am doing, I am loading this L1. You can see here. I am assuming I am loading this L1 into a register called A0. After loading it into A0, so this is the value of A0. This is the value of register A0. 0000, and in the last it is 101, 5. Then how can we check that this number is even or odd? So for that, what we can do, we can perform AND operation. And with what? 0000 001. We'll perform this one. After ending this, if the last value is 0, if the if the all value, if the value, the resultant value is 0, then we can say that the number is, we are adding with this 1 and 1 is 1. So what I am doing here, I am adding this one into a register, another register called A1. Then I am performing AND. and of a0 our value and this a1 which is just 1. So I am ending these two and I am storing the value in extend whichever return value register so that we can find. So here if the value is 1, it means it is even or odd. So if the value is 1 and 1 is 1, then the 1 means it is an odd value. If this value, let's say the number is 4, then it is 0, then the value this extend register, this is the value of extend register. Okay. If the number is 4, then it is a even number. So after adding with 1, it will become 0. So 0 means it is an even number and 1 means it is an odd number. Here we can see that 5 is an odd number. So when we run this program, you can say 1 here. It means it is an odd number. Let's say we'll use some even numbers like 60. I'm using 60 here. It is an even number. Then here the value is 0. Okay, so that's how we can check whether the number is odd or even. Okay, so I have another program. So yeah, I have one more program. I have one more program. So what this program is, basically this is a grading scheme. Like for we have a number marks of a student. Let's say it is 64, and we want to grade this student. Like if it is if the marks is above 90, then we'll assign a grade to it, and if it is greater than 75, then b. If it is greater than 60, greater than or equal to 60, then the grade is c. For 45 it is d, and for above 30 it is e, and for below 30 it is fail, f grade. So this is the program for this. So now we will see this. So first what we are doing in the data section, we are declaring this variable marks. Then in the text section, this is the main where main instruction are there. Then what we are doing, we are loading these marks into a variable a1, into a register a1. So I am getting this number into a1. Now we'll check for all these cases. So for case 1, if so what I am doing, I am using a temporary register T0 and I am assigning the value 90 to it for comparison. So we'll compare here. We'll use branch less than, and if A1 is less than T0, if our number is less than T0, then we'll jump to the case 2, means it is not greater than 90. If it is not this case, then we'll atomically run this instruction, the very next instruction. It means in extend, what I am loading here is 65. 65 means the ASCII value of A. So 65 means just 65 is equal to A, ASCII value of A. For A grade, I am using 65 here. Just this kind of. Okay, then if it is, we know that the grade is A, then we'll jump to the exit part. Exit part means exit of the program. Exit is the last level here, declared at the last bottom to exit the program. Then if it is not, when this condition is satisfied, that it is not the case that this marks is greater than 90, then we'll jump automatically here in case 2. Case 2 is here. Then we'll check it is greater than 75 or not. And if it is not greater than 75, then we will jump to here in case 3. And so on. case 3, case 4, case 5. I have made this one. So it is kind of, you can say, switch statement or if else. Now the number is 64. Here you can see. So it is of which category? It is of C. It should be C. We'll run this program and we can see 67. 67 is the ASCII value of C. Okay. So these are all, these are how you will use this RISC-V simulator. Formatting something. Okay, there is one more program to find GCD of two number. GCD means HCF. First, are you able to understand what I am trying to yeah, what I am trying to teach you? Okay, because the number of students are very less at starting. Okay, okay, okay. If you have any doubt, you can ask anytime. You can raise your hand or you can type into the chat box. Okay. So now I am using GCD of two numbers. So for to calculating GCD, first you have to know the basic C function for it. So to calculate GCD of two numbers, let's say X and Y. So GCD is if both these number are equal, X is equal to Y, then we return the number. If the number is equal to, then it is the base condition for this function. And else if it is not equal to, so if it is not equal to, then if X is less than Y, if X is less than Y, then we again call GCD. And now what we will do, we'll X is less than, so we'll use X comma Y minus X, if I'm not wrong. And for else part means if you can say Y is less than X. For this condition, we'll use GCD X minus Y and Y. This is the program. Now we'll convert this function into assembly language. Okay. So here there are two numbers, num1 and num2. In data section part, you can see here. And what I am doing in text part, in text section, what I am doing is I am load word. I am loading these two numbers into A1 and A2. These two registers I am using here, A1 and A2. Then this is the GCD function. So first we will check that. What I am doing here, I am checking that in which condition it will goes for first one, second one, and third one. So I make case one, case two, this kind of thing. Case one means if X is greater than Y, then we will call case one. So these are two number X1 and X and Y, A1 and A2. So if A1 is greater than BGT, I am using BGT here. If A1 is greater than A2, X is greater than Y, then we'll use case 1. And if in the another case, X is less than Y, if A1 is less than A2, then we'll use case 2. So here I have defined case 1 and case 2. This is case 1 and this is case 2. And if none of these means both these are equal, then we'll just exit. Exit means because uh, it is the same value. If x is equal to y, then return x or y. This is our GCD. Okay. So in case 1, what we are doing, we are just uh, subtracting this x minus y. We are using x minus y and storing it into x. Then I am calling here GCD function again. And in case 2, you can see x is remain same, but in a2 means in y, what I am doing, I am minusing, I am subtracting y, x from y. It is y minus x, and I am assigning it to y. Then I am calling this again x and y. This is the simple case. And in exit, we have at last we have x is equal to y, so that either we can use a1 or a2 here. So this is the value of our GCD, a1 or either a1 or a2. So I am adding 0 to it and assigning it to x10. So that the value of GCD will be stored here in register x10. So now I am calculating for 5 and 10. Let's run this program, and the value is, you can see here, is 5. The exit code is 5. If we use here, let's say 6 and 18, then the value is 18. You all know. Let's say, yeah, then the value is 6. You can say here, exited with the error code 6. It means that register x10 is storing the value 6. Yeah, this. Okay, so I think I have done so much programs. So let me discuss it once more. So these are the all these instruction address, integer instructions. Here you can see add I, and I, and all these things. These are here. You can find all the instruction and their descriptions. Okay, so in add, what you can see, we are using 3 registers. RD for destination register, RS1 means source 1 register, and source 2 register. So we are adding source 1 and source 2, and we are assigning it to the destination register. So this is the description or of add. And you can see here the description of all the instructions. These all instructions are integer types. These all. So you can find any instruction here. Then for floating point instruction, you can see it here. These are the floating point instructions. FLD means floating point load or floating point store, floating point add, floating point subtract. You can find it here, and their descriptions. And here you can see some complex instruction like multiply, division, these kind of things. These are here. If you want to multiply two numbers, divide two numbers, etc. What will the exit code when there is an error in the no, if there is an error, then the program is not compiled. That is the case. Exit code is nothing. Exit code is the I already said that exit code is the value of extend register. It doesn't mean that it is an error or not. It just represents the value of extend register. Yeah, I am using extend register, these extend register every time, because it is easy to see the output of the program. That's why I am using this extend register. After running, we can see just in the bottom left, bottom right. So here in this sheet, you can also see this core instruction formats. This is the instruction format. You can see here. There are different type of instruction. R type means register type, I type immediate instructions, S type, it is I think it is for to store, for all store instruction are of this type. This is for branch instruction, U instruction, UG instruction. These are all instruction type. This is the format, like this is the opcode for that instruction. This is the from bit 7 to bit 11, it is the destination register. and from bit 12 to 14 it is function 3. Function 3 is just function 3, function 7 you can see here is just the sub opcodes. You can see, let's say opcode, this opcode means the arithmetic operation, then function 3 will define that it is subtract or add, this kind of thing. This is not exactly same, but yeah, you can see it here. And immediate field means the offset value. What is the immediate value we are using in let's say I am using add I, and I am using x10, x0 and 5. So the 5 is that the immediate value here I am using. So I, this is the I instruction means add I is the is of this type I instruction. And you can say these pseudo instructions here, b q z, these are not the basic instruction. La, load address, which I am using, which yeah, I used in the program la. So it is not the basic instruction, it is in the pseudo instruction. It composes of two instructions. So here you can see which instruction, basic instruction they are using. So la is using au ipc, we have already seen this. So that la is using au ipc, and these are the pseudo instruction. And it is a good practice if you do not use pseudo instruction and use the basic ones. So can you please share this video? Yeah, I will share after this lecture. And these are all the registers and their functionalities. You can either use the that this x0, and you can use these names or also in the program. And here you can find the use of the these functions. And here you can see that caller callee means caller is the function which call some function, and call is the which is called by that function. So this is just these kind of thing, register and their uses. And here you can find the floating point standard. Like if we use floating point numbers, then how we'll represent the floating point into the register, how we'll represent the floating point into this is 16-bit register. If it is if we are using half means 16-bit, so how we'll represent it into the memory, the floating point value. If it is this 32-bit or 64 or 128, then how we'll represent it into memory. The formula is here, -1 to power s is here, 1 plus a. This is the mm, this is the formula to calculating the value of that floating point number. Then this is the memory allocation. I have already explained it to you. And these are the opcodes. Like for this is load byte. If we want to load a particular byte from the memory, then we'll use this load byte, and this all these things. AUPIC, the what is the this opcode of all these instructions? These are written here. What is the opcode and function 3, function 7 values? You can see it here. So I think the time is up. So yeah, I will share this PDF with you. So if you have any doubts, you can ask. Let me. Okay. So do you have any doubts? What is the significance of exit? This is what I am telling you. There is no specific kind of thing like this simulator is returning. So exit code is just the yeah, just the value which it have extend register have. So this is the exit code. It is not like do not think it in that it is a error or not. So it is the return value of the function. We use extend, yeah, we use extend for storing the value of return address. And we are seeing here at the bottom the value of what extend stores at last in it. Yeah, any other question?
Bharat, if there are no other questions, then maybe we can stop here.
Yeah, yeah, yeah. Yes.
Okay,
Okay. I am
so if
stopping.
they face any more issues related to this tool, simulation tool, then maybe they will send you email.
Yeah.
And very soon I'll share the Excel sheet with all the students that there are five TAs and it is not possible to answer all the queries by a single person. So yes, initially during your installation, if you face any issue, then Bharat will help. But after that, I will assign a particular TA to you, and for all your doubts, you will send email to that TA.
Okay, okay.
Uh,
I will share these all
yeah,
these
Bharat will
program into WhatsApp.
share
Yeah.
all the shared programs and the document also, that
Yeah.
PDF you will also share on Google Meet. Okay.
Yeah.
Okay, so I have to leave now. So I know I'm not sure if I leave. Maybe I don't know if you can stop the recording or not. So I'm stopping the recording here,
Yeah.
and then I think there are no other queries also. So we can stop after recording. We can
Yes,
stop
sir.
the
Yes.
meeting also.
Yes.
So let me first stop the recording.
Okay.
Okay, thank you, Bharat.
Yeah. Thank you.